Everybody, in this video, what I want to do is go over some stuff that's pertinent for your quiz 9. That's how to build a truth table. I'll also do another one on how to build a truth tree as well. There is a PDF called How to Build a Truth Table that explains a lot of this stuff in detail, but I want to do a little bit of a video on it to get you started. So first of all, what's the purpose of a truth table or a truth tree? Well, as some of you may have experienced on some of the quizzes that you've had already this semester, sometimes it might feel, well, hey, can this proof be done? It feels like it's impossible. What a truth tree or a truth table allows you to do is see if the argument is valid before you can even start it. You know, is this provable, or is there something going on here where this actually doesn't work? Truth tables and truth trees are two methods that allow you to do that. I personally find truth tables easier to do on really short problems, and I think truth trees are easier to do on longer and more complex problems. And we'll see here in a moment. I have two arguments on the board. Now, normally we do this in a proof format. What I'm asking here is, can we do a proof for it? Can we do a proof for this one? And can we do a proof for this one? Now, this is arrow out. This is something we know we can prove it. We're down in line 3. You know, arrow out, if we have A, arrow B, and A, can we get B? Sure, arrow out 1 and 2. This one, on the other hand, can we prove this? Now, I'm going to go ahead and tell you right now, no. This is even though it looks a lot like arrow out or modus tollens, it's kind of mixing up both of those. This says if we have an arrow and we have the right side of an arrow, we can get the left side by itself. Is that true? Nope. In fact, it's a fallacy called affirming the consequent. You can't do that. It's not going to work. Well, if you're like, well, how do I know that it doesn't work? If you try and prove this, you'll be stuck forever. There's no rule to allow you to get this from these because it would be invalid, at least deductively. So here's how you do a truth table. You lay out your premises like this, okay? And I'm going to number them. So this is premise 1, this is premise 2, and this is the conclusion. Okay, now, the first thing I like to do is label my parts. So in this problem, we have A and B. Those are our only constituents. That is, by constituents, I mean letters in the problem or values that we have in the problem. And then what I want to do is tag every possible truth combo that I could have for these values. So I want to think of the instances of this being true and this being false. What's the scenario that would make this not work? So let's take a look at this. Now, mathematically, I'm going to say however many values that you have, you're going to have that pretty much, well, we'll just say, we'll start with this. If you have 2 values, you're going to have 4 rows. So look, this is how I'm going to start. TTFF, TF, TF. Now, in short, what's going on here is here's where A and B are both true, here's where A and B are both false, and in the middle here I have every other possible combination. That's the only thing that needs to happen, okay, with these. So I'll just put it this way. If you're doing a truth table where you have 2 letters to deal with, A or B or X and Y or whatever, it's going to just make it look like this, okay? Now, that's every possible truth combination that we could have. Then what we're going to do is we're going to look at the truth table rules to see the values of the premises. So for these are simple statements in the second premise and the conclusion. What I'm going to do is just copy and paste these values over. So for A, it's going to be TTFF. For B, I'm going to copy and paste that over. TF, TF. And then for A arrow B, what I need to do there is consult my truth table rules. And so what I want to do is this. I want to figure out when is this arrow true or false. Now, if you look at the truth table rule, you'll see that the only time that an arrow is false is when you have a true left and a false right. Every other instance of an arrow is true. So this is the way this is going to look. I'm trying to figure out what are the truth values of this. True left and a true right, that's a true arrow. True left and a false right, false arrow. False left and a true right, that's true. False left and a false right, that's also true. Let me give you an example. If you're wondering, why does that work? Well, consider this arrow statement. If my son cleans his room, I'll give him ice cream. Well, think of this. If my son cleans his room, then I'll give him ice cream. Well, that's true. If my son cleans his room, then I don't give him ice cream. If I say to my son, if you clean your room, then I'll give you ice cream, and then he cleaned his room and I didn't give him ice cream, that would make me a liar. That would make that a false statement. But if I said to him, you know, if you clean your room, then I'll give you ice cream, and he doesn't clean his room, I can still give him ice cream anyway. And then in the last instance here, you know, if you don't clean your room, then I won't give you ice cream. Well, that's a true statement as well. So that's the way that arrows work. Here's all you need to know. Table rule, true left, false right, that gets you a false arrow. And then what we want to do, like why did we punch all this stuff in? Then think back all the way back to quiz 1. What's the definition of validity? An argument is valid if and only if, given all the premises are true, it's impossible for the conclusion to be false. So now what I want to do is I want to look at every instance where the premises are true. And I'm going to do this by row. So look at this row here. Look, the first premise is true. The second premise is true. What do I see over in the conclusion? It's true as well. That means that this argument is 100% valid. You can do a proof for it. In fact, that proof will just be arrow out. There are some other things you could do, let's not. What I want to do now is take a look at this argument and evaluate it. Premise 1, premise 2, here's the conclusion here. So we can say, based on what I have up here, yeah, this totally works, it's valid. Let's take a look at this one. I'm not going to rewrite A and B again for the sake of space, but I'm just going to copy these values over still, and even the premise is the same as this one, so I can really, for this argument, just copy over a lot of stuff. We know that's going to be the values for this premise. We know that's going to be the value for this premise. And we know the value of A is going to look like this. Okay, looking at those, because those are simple statements. And what I want to do again is the same exact process. Look at the instances where the premises are all true, because we're trying to figure out, is this a valid argument? And what a valid argument means, if the premises are true, it's impossible for the conclusion to be false. So let's take a look at this row, for example. Look, there's a true premise. True premise. What do we have over in the conclusion? It's true. Lest you rejoice too soon and say this argument is valid, look, there's actually another row when the premises are true, but the conclusion is false. What does that tell us? That means this argument is invalid. That means, given that the premises are true, it's possible for the argument to be false. The great thing is about a truth table is it also tells us when. So if I look back over here at my constituent components, this right here, and I could have rewritten this over for this one as well. When A is false and when B is true. So we can put it this way. It's invalid when, and this is called the counterexample. This argument is false, does not work when A is false and when B is true. That's one way of writing it. Another way I could write it, the counterexample, is that if you got a not A and a B, that's when this argument does not work. It will not work under those circumstances. So it tells us you can't prove this. There's no proof for it. And also says exactly when it doesn't work. And you'll see that even when getting more complicated, that's all we're trying to do with truth tables is look at this method for figuring out, can you do a proof for it or not? If it's valid, you can. If it's invalid, you cannot. There's no proof, there's no way, there's no how. And this tells us exactly why, because there are instances where, yeah, sometimes this works, but sometimes it doesn't. And that's all you need for something to be invalid. Not that for something to be invalid does not mean that it can never be true, but that it's possible that it might not be. Okay, like if I say something like, it might rain tomorrow, that's not deductively certain. That's not apodictically certain. It might not. There's no way I could have 100% certainty there. So in the next video, what I'm going to do is talk about truth trees a little bit, which is another method for doing the exact same thing. Okay, different set of rules. That's what your quiz 10 will be on.